So when it comes to us, I was only able to hear 2 of those things. That was it. I couldn't go past 2 of them. My ears are just getting too old and starting to become very damaged. And you saw that when it comes to audible sounds, the high pitch sounds or those sensors, those hair cells are closer to the outside of your hearing or your ear. So those get damaged. They don't replicate. They don't grow back. And so you lose that hearing. That's the reason why. The other thing that we have here is that the speed of sound actually depends on the medium that the material is going through or the sound is going through. We know that medium is the material or the disturbance, right? Sound can travel through a solid, liquid, and gas molecules. Sound can't travel through a vacuum like outer space. Okay? Cannot travel through a vacuum like outer space. When you're ready, we're going to turn the page because we definitely need to know this paragraph. There's a question on the quiz. We definitely know that sound has to travel through a medium. It cannot travel through outer space. That's a question on the quiz. But here's another question on the quiz. This one right here. You're going to receive this chart. I'm going to zoom in on the chart. You can see the chart on your paper. Let's look at this chart. This chart is different mediums or different types of matter over here. And so when it comes to these different mediums or matters, you can see that gases are generally slower than liquids versus solids. Solids are generally the faster ones, okay? So solids are faster to transfer sound, and gases are a little bit generally slower, okay? Now, what you're going to do for the quiz and on the test is you're going to have to calculate the velocity. They're going to give you a frequency, and they're going to give you a lambda, and you need to calculate the velocity. Use the chart to find which matter or medium it's traveling through. Easy cheesy? I think we can do that. Let's go ahead and fill in the blanks now. It says over here, well then on letter C, if sound cannot travel through a vacuum, what does that say for an example like Star Wars movies? How are they inaccurate? They're inaccurate because we can't hear sound in outer space. They're inaccurate, but I want to pause for a moment because what about the people in the ISS, the International Space Station? When they're contacting people over here in Clear Lake, NASA, and they're talking to them, how can they talk and sound can travel from outer space in a vacuum all the way to Earth? Well, if mechanical waves, which is what this unit is talking about, must have a medium to travel, do you remember the electromagnetic waves? They don't have a medium to travel. So that's actually how we communicate with the ISS. We use electromagnetic waves or radio waves, which don't have to have a medium, so that way we can hear people in outer space. Okay? Let's keep going here. Sound waves consist of particles that are going to vibrate, and the speed of the wave depends on how quickly one particle can transfer energy to another. Sound generally travels faster through solids. We just saw that in the chart. Then through liquids or gas molecules. In solids, the particles are closer together and they can transfer faster because the particles are right next to each other, smushed together in a solid. There are some solids that actually can slow down or stop sound like foam or rubber. And you can see that over here. Look at this rubber. Look how slow that is compared to the other solids. These solids can be used for soundproof. You know, like you're in a choir room and they have all that foamy stuff on the sides of the wall to stop the sound from traveling. Alrighty. Other than that, I'm going to turn the page. Like I said, my goal is to hit as much stuff that is on the quiz tomorrow. And then we can hit a little bit more notes before we take the quiz tomorrow and then next week finish off for the test. I am going to turn the page to this part over here, and we are getting close to the end. Sound intensity. There should be a question, if I recall correctly, regarding the intensity of a sound. Sound determines, it says here, what determines the loudness of a sound? The loudness of a sound depends on the amount of energy a wave contains. The amount of energy can be determined by the amplitude. The bigger the amplitude, the louder the sound. Okay, stop and think about it for a moment. Have you ever been to the point where you are gonna yell at somebody? And when you yell at somebody, what happens? You have to use a lot of energy. Like, I'm yelling at you and all of this energy, and it's exhausting, versus using an inside voice, less energy, a smaller amplitude. So here we go right here. I'll come back. Let's come over here. It says, let's go ahead and draw what a sound looks like. Remember, a sound looks like a spring or a slinky. This is what a sound is going to look like. But if it's a loud sound, it's going to have a big amplitude. So the amplitude is going to look like this. It's going to be further from the equilibrium. This is a loud sound with a lot of energy. If this is my equilibrium in the middle, that amplitude or the distance from the equilibrium is big. I can see it right here. But if I'm going to produce a soft sound, my amplitude is going to be close to the equilibrium. It's a really soft sound. Look how little those little amplitudes are. They're close to the equilibrium. Right there. It says here on the next question, what's the difference between the two waves? The difference from equilibrium is what the difference is. The difference from equilibrium between the two waves. Loud waves have a large amplitude. and soft, quote unquote, waves or sound have a small amplitude. Okay, makes sense? That's a quiz question. We'll be ready for that tomorrow. The next one, I'm going to scroll back up, so I'm going to move the paper down so I can go back up to the top. Intensity depends on the energy of that sound wave. Loudness, in human perspective, when you hear a loud sound, we call that the intensity. The intensity is measured in an SI unit. Loudness has an SI unit called a decibel. One more time. A loudness SI unit is a decibel scale, the decibels. Traditionally, 0 through 70 decibels is what we can hear. Like, that's good. 70 is super loud. You're at a major concert, you're probably even right next to the speakers. That is loud. Pain threshold. You can handle about 100 to 120. Most people can handle that. After 120 decibels, it starts to physically rupture your eardrums and your ears start to bleed out. You're in actual physical pain. Not like those mosquito ringtones that are like annoying to listen to. Not annoying, pain. Greater than 120, your eardrums are going to rupture and they start to bleed out. You're physically, it feels like somebody's stabbing your ears. Okay? Next part. You're like, all right. Here we go. Resonance. Now, resonance is a super important word here. Okay? Resonance is going to be a word that we actually have seen before. It is the ability of an object to vibrate by absorbing energy at its natural frequency. Let me give you an example. We have a tuning fork, and we put the tuning fork after we hit it, ding, next to some salt that's on top of a cup. When we put it next to the salt without touching, the salt starts to do what? Move. Why is the salt starting to vibrate? Because the tuning fork that had a frequency was able to match the natural frequency of the salt, and it transferred its energy to the salt. The energy started to vibrate, or the salt started to vibrate, because the energy was transferred to the salt. Turn the page when you're ready. And we're going to skip down to number 4, the Tacoma Bridge. This is a true video you're about to watch. It says here, what happens to the bridge when the wind provides an external frequency that matches the structure of the bridge? You need to fill this in once you watch the video. Alrighty? So let's watch this.